I'll begin with a word of prayer. Dear Father, we thank you for this day, lovely weather, and for the weekend we're about to start. Just pray you be with us today, help us to glorify you, what we do, Lord. In your name I pray. Amen. Okay, so today we're talking about inner product spaces. I suppose we have a few more things to say here and there about eigenvalues and eigenvectors. Those will come in due time. But we're more or less done with that. There is an exciting place where these two worlds sort of collide and we find an interesting theorem called the real spectral theorem, but that's about 4 lectures away. So to start with, we need to talk about what's an inner product space. And in short, what an inner product space is a way to give a vector space something that is abstractly like a dot product. So the most basic example of an inner product space will just be Rn with the dot product. Okay. So what is an inner product? It's a map. You give it a pair of vectors, x and y, and it outputs a scalar in your field f. Now the field, we're either going to look at the reals or the complexes. That's it. All right. But this inner product, which we use angle bracket, like this notation here, right? It has a few important properties. One important property is that it has linearity in the first slot, which is my A and B together. So linearity in the first slot, these first two things. So you can break up addition in the first. We can pull a scalar out of the first component. And then here, this bar denotes complex conjugation, right? So this is, in the case that f is equal to the reals, what does part C become? We just have xy equals to yx, right? In other words, C becomes just what's called the symmetric property, that inner product of x with y is equal to the inner product of y with x. That's in the case that the field is real. And then finally, the inner product of any vector with itself is positive, provided that the vector is non-zero. Right? These are the axioms that give you what's called an inner product. If you take a vector space, all right, and you pair it with an inner product, it's called an inner product space. All right? So without further ado, let me give you some examples. Number 1, V equals to Rn, with the inner product of x and y just being equal to x dot y, where x dot y is the usual dot product. This is an inner product. You can do weird stuff. You could take V equals to R2, and you could define the inner product of, say, vector A and vector B to be something like A1, B1 plus 2 times A2, B2. This would also define an inner product on R2. You could check these axioms. You'd get all of the necessary ingredients. If we look at the complex n space, Cn, so that's, n complex vectors, you can define the inner product here of z and w is equal to z w star. Now, I have used star as a couple different things in here. At this point, I have to make a decision. I can no longer vacillate on my definition of star. Here, star, w star, is equal to the conjugate transpose. So we use bar for conjugate. We'll use transpose for transpose. So the star there is conjugate transpose. All right? So this, you can pretty easily check. It's quite obvious that A and B work for this definition, right? But maybe C is a little bit interesting. What happens if you take the complex conjugate of this thing? So how does it work? The complex conjugate of the product of two complex matrices, well, it's in fact the conjugate of This is a property of complex conjugation. But let's see here. What is this? That is Z bar W bar bar transpose, because you can either take the transpose or the conjugate in either order. I mean, this is a property. So anyway, that gives you Z bar W transpose. But this is a complex number, right? Which is a 1-by-1 matrix. So you can say that this is equal to its own transpose. Right? What's the transpose of a number? It's the number again. And so, but then sock shoes is kind of interesting, because that makes W Z bar transpose, and W transpose transpose by sock shoes. And what is that? That by definition is WZ. So there you go. That shows you that this new, I suppose, inner product is satisfying what we want. So this is a verification of axiom C for the usual inner product of complex vectors. It's probably useful to take a second to unravel what 3 looks like in more detail. Oh, so, okay, so if you have Z with W, in other words, we're looking at, you know, Z1, Z2, Zn, inner product with W1, W2, Wn. What does that actually, what's that formula actually mean? So it works out to Z1, W1 complex conjugate plus Z2, W2 complex conjugate plus plus Zn, Wn complex conjugate. That's what the formula I just wrote down looks like when we look at it in terms of components of the complex vectors. So, for example, if we look at the inner product with a complex vector Z with itself, what that reduces to is Z1, Z1 bar, Z2, Z2 bar, Zn, Zn bar, which you might recognize as what? Modulus of Z1 squared plus the length as a complex number of Z2 squared, length of a complex number Zn squared. So, yep.
Can you explain why there's no transposes for the W's?
That I worked it out. I mean, that's what this product would mean. So this is, what is this? This is equal to the row vector. This is equal to, wait a minute. I wonder if I've got a, I don't know. Huh. Oh, now you've worried me. Let's see here. So that would be, I think it'd be the, oh no. Right? Assuming that W is a column vector, that would be what? 1 by n. Oh, man. Oh, idiot. Me, not you. Dang it. I copied that down wrong. Oh, stink. The formula is actually W star Z, which can also be rewritten as Z transpose W conjugate. Sorry about that. Well, now my calculation is now formal nonsense. Unfortunately, these same steps are actually true, but with the right formula. I mean, Well, that would have been an awesome question about 5 minutes ago. Let's see here. So, all right, fine. So ZW is conjugate is W star. Well, let me just get straight to the point. It's Z transpose W conjugate conjugate, which is Z conjugate transpose W conjugate conjugate, which is, of course, equal to the transpose of that, because it's a 1-by-1 matrix again, now actually for real. What I had written was actually n by n. Anyway, so W transpose, Z conjugate transpose transpose, also known as W transpose Z conjugate, also known as inner product of W with Z. All right. So, sorry, yeah, I just didn't notice the order of letters in my notes when I copied it down, and sorry about that. Anyway, this formula is still correct. Okay. So, the interesting thing here, of course, is that we can pull scalars out, like complex scalars out of the first component, but when you pull a scalar out of the second component, you can't just pull a complex number out of the second entry to the complex inner product, right? Because there's this conjugation going on. Okay, moving along. Finally. Oh, sadness. Sadness, sadness, sadness. 4. How do you guys think we should define the inner product of two matrices? Suppose that these are both n by n matrices. How about this? We just think of them as n squared dimensional vectors and just calculate their like usual Euclidean products. So it'd be like A11, B11 plus A12, B12, right? Plus finally ANN, BNN, right? I mean, that seems like a reasonable dot product for two matrices if we're going to do something that's an abstraction. There you go. Now, the neat thing here is if you rewrite that, you can there's a really slick way to rewrite this. This is actually the sum over I and j, right, equals 1 to n of aij, bij, right? Which, of course, we could rewrite as the sum over I and j of aij, bji, B transpose ji, right? But what's that? That's nothing more than the trace of AB transpose. So if you want to prove something about, n by n matrices as an inner product space, using this notion of inner product, then which formula do you prefer? The one I wrote last or the one I wrote to start with? I mean, the one I wrote to start with is totally natural, right? If you take the inner product of 1, 2, 3, 4 with 5, 6, 7, 8, that definition says it's 1 times 5 plus 2 times 6 plus 3 times 7 plus 4 times 8. Well, great. That's actually how I would calculate that. But to prove something theoretical, the formula I wrote at the bottom is much preferred, right? For example, to see that this inner product is symmetric, we know properties of trace is what? Trace of what? Yeah, this is the trace of B transpose A, right? Because we have the trace of AB is equal to the trace of BA, right? You guys proved that a while ago. Now here's one you might not have thought about. Is the trace invariant under transposition? I mean, I might have, this might be dumb. I might just go back to where I started. I'm not sure. But this should also be equal to the trace of B transpose A transpose, right? Which would be what? Oh, no. I'm sorry. I'm an idiot. Let's start this again. Let's not do what I did. So this would be equal to the trace of AB transpose, right? Because if you transpose a matrix, it doesn't change the trace, right? The diagonal is fixed under transposition. And so, but then by Sock's shoes, this is what? B A transpose, which of course is by our just now given definition, B comma A. So there you go. There's a proof of symmetry at that. Of course, I mean, you can prove symmetry with the other formula I gave here, pretty much just the same, right? If you look at this formula and you just commute everything here, you'd have a proof of symmetry just the same, all right? So I don't know. But anyway, this is the so-called Frobenius inner product for Rn by n. All right, so this makes Rn by n an inner product space. Example 9.1.7, we could look at complex n by n matrices, and we could let the inner product of Z and W, two complex n by n matrices, be equal to the trace of Z W conjugate. Oh, that of course is again the conjugate transpose. In physics literature, that's sometimes called the dagger. So sometimes in physics, you'll see this. This is W dagger. I think I should make a proper dagger. I don't know here. Okay, anyway. So Hermitian conjugation. Actually, conjugate transpose. But anyway, that gives n by n complex matrices the structure of a complex inner product space. Now, this next example is a little bit more out there, but we can look at continuous functions rather on 0 to 1. So continuous functions from 0, 1 to the reals, all right? And we could define the inner product of f and g to be the integral from 0 to 1 of f of x, g of x dx. So of course, to check it's actually an inner product, we have to sort through the axioms, right? It's a real inner product, so we're looking for symmetry, linearity in the first component. You pull a constant out, right? So the linearity and the symmetry are pretty much obvious from the formula, right? If I replace f of x with like f1 of x plus f2 of x and a constant, you can see that pretty easily, right? Cf1 plus f2 comma g, integral from 0 to 1 of c times f1 of x plus f2 of x times g of x dx. Properties of integration we learned in Calculus 1. Pull the constant out. And that gives us c f1 comma g plus f2 comma g. So there you go. That gets us both a and b proved in one foul swoop, right? Because a and b we can summarize as basically linearity of the first slot, the first entry in the inner product. How about symmetry? Symmetry is almost obvious, right? So this is equal to the integral from 0 to 1, right, of g of x f of x, which, by the way, is g comma f. So there you go, symmetry. So what's left? To prove that that's an inner product on the set of continuous functions, we also need part D, right? So suppose, think about this for a second. Suppose we had that the inner product of f and f, which is, by the way, the integral from 0 to 1 of f of x squared dx, suppose that was equal to, suppose that was not equal to 0. and yet f of x was equal to 0 for all x, right? In 0 to 1. Is that possible? Can you have a function, a continuous function, whose integral is 0? The integral, not the function itself, but the integral of the square of the function is 0, right? I mean, is non-zero, and yet the function is 0. See? Suppose the integral of the square of the function is non-zero, and yet the function is everywhere 0. Could you have that? Certainly not, right? So in fact, let me put it more directly. If this is equal to 0, then what does that imply? This implies that f of x is equal to 0 for all x in 0 to 1. Continuity is needed there, right? Because continuity says that if the function is non-zero at one point, it has to be non-zero near that point as well, right? And so non-zero at a point and nearby means that when you look at the square of the function, there's a finite area, which is going to be calculated by that integral, right? So we have to have that the function is 0 if the integral of the square of the function is 0. So that's axiom D. And so you could try to use this same definition for, say, continuous functions on the reals. Take the domain of the function to be the reals, right? And still try to use the integral from 0 to 1 of f of x dx, f of x g of x dx equal to the inner product of f of g. You could try to do that, but you'd fail. Not because, axioms A, B, and C, they're still fine. It's still additive, full constants out, it's symmetric, but axiom D fails. Because you could have a continuous function, right? You could have a continuous function on the reals whose integral from 0 to 1 is 0. The integral of the square of it from 0 to 1 is 0, and yet the function is non-zero, right? Can you guys tell me what that would look like? So here's, this much is required. I do need that the values of the function from 0 to 1 are 0. But what could I do beyond that? Whatever you want, right? The inner product can't see that. The inner product only sees from 0 to 1 here. So if I go beyond, if I let it be 0 all the way out there, but over here I go wee, like that, then that's not the 0 function. And yet the inner product of that function with itself is 0. So that violates D. That's why the integral from 0 to 1 of f of x times g of x dx is not an inner product for the set of continuous functions, even though it is an inner product for the set of continuous functions on just 0 to 1. Here's an interesting thing. That can't happen for polynomials. So despite the fact that polynomials have a domain, which is the whole reals, this integral from 0 to 1 still serves as an inner product for the set of polynomials. So if you say, instead I'm going to use v equal to r of x thought of as functions, then it still works. Because you can't create this bump function example I just showed you guys for polynomials. Why do you think that is? Well, that's more a question of calculus than linear algebra, so I'm going to go on. All right. So we have properties. So again, V and inner product. First of all, in fact, if you have what we already have, you can prove that we also get linearity, additivity in the second slot. You can also prove that generically speaking, if we have x times cy, we'll get the complex conjugate of c times xy. Of course, in the case that the field is just real, we just pull out a plain old scalar, because c bar is just equal to c if we're working with the real field. All right? C, inner product of x with 0 is equal to 0, which is, by the way, also equal to the inner product of 0 with x. D, we have the inner product of x and x is 0, if and only if x equals to 0. And then E, if xy is equal to xz for all x in V, then guess what? Y is equal to z. So part E to this story is sometimes called non-degeneracy. Right? It's kind of a cancellation property, all right, for the inner product. So we should prove one of these. I'll let you guys pick. Anything but E. Yeah.
I actually just have a quick question.
Go for it.
So, like, you said if it's not overly complex, then we just pull out a scalar, right?
Yeah. Well, we just pull out C rather than, I mean, C bar is equal to C.
So
If
you
we're-
were to see, like, a scalar in front of an inner product, does it matter which element you put that scalar in front of, since we've already established that?
It does matter, because if I have 2 plus I, and I'm looking at a complex inner product, then this is equal to 2 plus I times z, but it's equal to that's what this proposition means in an example.
Those two expressions are equal, so
They're equal, yeah, but you can't just pull the scalar into either slot unless you adjust it appropriately.
right.
So you may have been saying that, and that's fine.
But
yeah.
if it was a real, the scalar out in front.
Yeah, if it's a real inner product space, we can bring the C into either slot, just like a dot product. So the real inner product is just like a dot product. The complex inner product is a little bit unfamiliar because of this not quite bilinearity. Sometimes people will call it sesquilinear. It's like 1.5 times linear, because you have additivity, C, in both slots, one by definition, one by proposition. And you can pull constants without consequence out of the first one, but the second one, you pull complex conjugates of the constants out. That's foreign to our experience so far, admittedly. So which one do you want to prove? A, B, C, D, you pick. Not D. A, B, or C? No, not B. A or B? A, okay, there we go. Let's see here. So what we'll do is we'll look at x comma y plus z. All right. We'll take the conjugate of that, complex conjugate of that. What's that going to be? Right, by part C of the definition, we do that. But then we have additivity in the first slot, so this is what? Right, and then, well, take complex conjugate of star. Let's call this star. So we get x comma y plus z conjugate, right, is equal to yx plus zx conjugate. But by the properties of complex conjugation on a complex vector space, we have by assumption, of course, that the complex conjugate of the complex conjugate is, again, where we start again. So that's just x comma y plus z. And here, of course, we've got so part of the property of complex conjugation is that I can break it up into the sum of the conjugates, right? But then again, I use part C again 2 times. So we got x comma y plus x comma z, and there you have it. That is the desired additivity in the second slot. And the proof of B is somewhat similar. So, okay, great. Now, so actually, everybody have this down? Okay. So inner product spaces in and of themselves are, of some interest. But to really complete the story, we have to talk about the norm. So a definition. And so what I'm about to give you a definition for here, if I can find my notes, is the so-called norm, which is induced from the inner product, or also known as the induced norm. All right, so here it is. Let V paired with inner product be inner product space. All right, then we define norm of x in V by double vertical lines x equals to the square root of inner product of x with itself. So this defines the norm of a vector. The norm, this is also, norm sometimes we'll replace with also equivalent to vector length. So the norm is the length of the vector, right? So this is pretty exciting because it's going to mean that if you take 2 different vectors in an inner product space, you can just look at the displacement vector that connects those 2, right? And you can calculate the norm of that displacement vector, and that will give you the distance between those 2 vectors in the complex inner product space, or the real inner product space. That's what we do in physics, right? We take 2 different position vectors, you calculate the displacement vector from one to the other, calculate the length of the displacement vector, that's the distance between the points. So this is a generalization of that for arbitrary vector spaces over the reals or complexes, provided that you've got an inner product on them. By the way, you can put an inner product on any finite dimensional vector space. It's not hard to do. But one thing at a time here. What are the properties of the norm? Properties of induced norm. So part A, if we have the norm of a constant times a vector, what does that give us? How about part B? If we have the norm of a vector is 0, that's true if and only if what we can say about the vector. Part C, the absolute value of the inner product of x and y is less than or equal to the norm of x times the norm of y. Part D, the norm of x plus y is less than or equal to the norm of x plus the norm of y. These are the 4 most important properties of the norm. In fact, well, I guess we need to finish writing this here. So how does this first one finish? So if we pull a constant out, we pull out so this is either absolute value, or it's the length as a complex number, depending on context. So Skimbortis will refer to both of these as modulus. Or he'll refer to both of these as absolute value. I try to only use absolute value for real numbers, But some people use absolute value to refer to the length of a complex number. Like the absolute value of 2 plus I is the square root of 5. In that way of thinking. So anyway, so absolute value of C times the norm of X. The norm is 0 if and only if we're looking at the 0 vector. So 0 norm is pretty awesome because if you have 0 norm, guess what? That's the 0 vector. And now C is what's called the Cauchy-Schwarz inequality. And this is the triangle inequality. I won't prove all of them, but I'll do part A. Let's do A. So looking at the norm of Cx, right? So that's the square root of the inner product of Cx with itself, right? But then, by properties of the inner product, that gives us C from the first one, C bar from the second one, and then X with X. This makes sense because C with C conjugate is a real number, a positive, well, non-negative real number, right? And, well, X with X is at worst 0, right? By the thing I just erased, it's either 0 or it's positive. I mean, it's a positive number by assumption here, right? So anyway, this makes sense, is my point. And then by properties of the square root function, we've got the square root of C bar, square root of X with X. But guess what? This is the modulus of C, or it's the absolute value of C, depending on what your context is, reals or complexes, and that is the norm of X again. So there you go. The proof of C and D are considerably more involved. All right? So naturally, that's homework. But the homework is guided. It's not just, I don't just push you out. I don't find a freezing pond and just push you in. I try to give you a path through the wilderness there. In the notes, there are proofs that are very much mired in the world of real dot product arguments. So there is some argument given in the notes, but they're not as general as I want. The more general arguments are traced out in your homework. Okay, so, notice this. If X and Y are not equal to 0, right, then what do we have? We have that the absolute value of xy divided by the norm of x, the norm of y, right, is less than or equal to 1. So this is true for f equals to the reals or the complexes. If we look at just the real case, then we actually can say more. We can say that minus 1 is less than or equal to the inner product of x and y over the length of x, length of y, less than or equal to 1. The complex inner product could be a complex number. So I can't strip off the modulus in the complex case, right? I can't write inequalities involving things like 2 plus I is frowned upon generally. Doesn't make sense. But of course we have inequalities for real numbers. The modulus of the complex inner product is a real number, so I can say that much. And so in view of this, we can make some definitions for V over C with complex inner product. I define it as theta tilde. Cosine theta tilde is equal to the modulus of xy over the inner product of x and y. So this defines complex, quote unquote, I called it complex angle. There doesn't seem to be a lot of agreement on this, guys. Complex angle between x and y. And that's maybe not the greatest terminology because I'm not saying that theta tilde is a complex number. It's a real number. I'm taking the cosine of it, okay? where theta tilde is where? What's cosine look like? Like that, right? So theta tilde is an element of 0 to pi over 2. All right? Because I need that to come out to be a positive number, or possibly 0 at worst. On the other hand, if we have V is a real vector space, and we've got a real inner product, cosine theta equal just the plain old inner product of x and y over the length of x times the length of y defines angle theta between x and y. And there, of course, theta can range from what? Zero to pi. That's, of course, in agreement with the definition of angle that you were shown in Calculus 3 if you had it, right? We talked about the angle between two vectors. This is just a generalization of this. Now I can talk about the angle between two matrices, right? That 1, 2, 3, 4, 5, 6, 7, 8, those two matrices, we could calculate their inner product. We could calculate the angle between those two 2 by 2 matrices in this definition. All right? By the way, any complex vector space can be made into a real vector space, right? And you can also take the complex inner product and define a corresponding real inner product as well. That's in the notes. It's pretty simple. What you do is you just take the complex inner product and you just take the real part of it that ends up defining a real inner product in that sense. I have more important things to talk about at the moment, though, so I'm going to go on. So definition. If S equal to V1, V2, Vk is a subset of V, an inner product space, all right? Then S is orthogonal if the inner product of Vi and Vj is equal to 0 for I not equal to j. For all I and j. So in other words, pairwise, the inner products are 0. That defines S to be an orthogonal set. S is orthonormal if we have that the inner product of Vi and Vj is straight up equal to the Kronecker delta Ij. So notice that the condition, like Vi comma Vi equals to 1 means what? The length of Vi squared is equal to 1. So the length of Vi is equal to 1 in an orthonormal set. So an orthonormal set is an orthogonal set in which every vector has length 1. Which means, by the way, that an orthonormal set can it contain 0 if it's an orthonormal set? It certainly can't, because the norm of 0 is 0. Right? On the other hand, an orthogonal set in principle could contain 0, right? Check this out. 0 comma x is orthogonal. Why? Because the inner product of 0 with x is 0 for any x. Therefore, the set containing 0 and x is an orthogonal set. But it's not orthonormal, right? Because the length of x could be whatever it is. I mean, you could normalize x. How can we normalize x? How do you normalize x not equal to 0? I usually call it x hat. It's 1 over the length of x times x. That's a unit vector in the direction of x. So orthogonality doesn't by itself imply linear independence, right? Because 0 is a set containing 0 linearly independent. Certainly not, right? But you have to you really don't have to say much more. Here's a theorem. If S is an orthogonal set of non-zero vectors in an inner product space, then S is linearly independent. Here's the proof. So let's let S equal to, well, let's see here. Be careful. Suppose we have v1, v2, vn in S, right? Which is orthogonal. And we're assuming that vi is not equal to 0 for all I, right? How do we prove linear independence? We suppose that c1 v1 plus c2 v2 plus cn vn is 0. What's my goal now to prove linear independence? What do I need to do? You should be like, we've been talking about this since like week 3 in here. Could you stop talking about it already? We're bored of this. No, linear independence is always with us in here. It's always with us. Till the bitter end. Which is near, right? So how about this? Take the inner product of this. Take the inner product of that. With v sub j. So that's the inner product of 0 with vj. Inner product of 0 with vj, by the way, is 0. But by properties of the inner product, which, by the way, extend to finite sums just like they do for 2, we can pull the constants out, right? This simplifies to c1 v1 vj plus c2 v2 vj, right? Plus cn vn vj. So all of these inner products are by assumption what? 0. Except for 1. What's the one which is not 0? Cj with vj equal to 0. But this says that cj times the length of vj squared is equal to 0. But remember, we're assuming that vj is non-zero. So it has a non-zero length. So the only way that that can be 0 is for the jth coefficient to be 0. And that's for arbitrary j, right? Therefore, S is linearly independent. So orthogonality and non-zero is sufficient to give us linear independence. That is nice. So next time, I will explain to you guys just how amazing orthonormality is. We're going to find out if we have an orthonormal basis, which is what? A set which is both orthonormal and a basis. orthonormal basis allow you to just write down formulas for the coordinate charts by just taking dot products. I'm sorry, inner products. But it's just like we learn in Calculus 3, dot products have to do with projections. Inner products have to do with projections, it's the same. You get it.